Hello, this is Shravan. This is my video report for Game 470 Assignment 3. And let's get right to it. This is the first programming problem where we just had to separate out the camera matrices from the world matrix. So you can see everything's running. So if we go in the code, in the header file, first of all, to store the camera matrices, we create a structure. And so there's a design choice here that because the world matrix is the only thing that's left, so we don't really need to create another structure just to store the world matrix also. So these structures are basically to model the data that's going to go into the shader constants, which we have over here, the view projection buffer, and then the world mat will just take a world matrix. So over here, we just have one buffer that we're going to use for the view and projection. We have one that we just create a buffer and we pass in the size of a matrix, and we connect them to the render pipeline. So we've got two registers here, there's B0 and B1. So we connect them accordingly, initialize the world matrices, that's normal. And finally, in raw, so you set your view and projection matrices that we can send in, and the world matrix goes in separately. So yeah, that's it. And you can see that the scene renders as it did before. So all good there. There we go. Okay. So let's go to the second one. All right. So in this one, we had to create the unit pyramid. This is again a pretty straightforward problem. Come on. Wow. Yeah. All right. So yeah, tiny little pyramid, height, width, depth of 1. So in model tools.cpp, like I said, it's pretty simple. So 5 vertices, 6 triangles, and then we just set them up with the corresponding windings, and uncomment this part, and in the XApp just call a unit pyramid. So that gets us there. Pretty straightforward. In the third problem, we've got we have to render 3 models, I think, on the screen. Yeah. So let me just, wow, wish I could, yeah, come on. All right, so we've got 3 models up on screen. So what we do is we have this as before. The only thing we need to do is have 3 world matrices. That's the only thing that really does that. We've initialized the matrices here, so this is the only thing that actually controls the different positions. And then it's pretty simple. We have the constant buffers. We just keep updating it. So this is for the first one. Initialize the world matrix and a color. Update the constant buffer and render it. This is for the second one. Exact same thing. Different color, different world matrix, and the third one. Then you render it, and yeah, that's it. And then for the last one, this was the slightly tricky one. We have to use 2 different shaders. And yeah, come on. Go on. Okay, so 4 different objects. 2 of them are using the simple color, 2 of them are using the color selected. And so the way that we do it here is that we basically need 2 buffers for each shader. We've got those here. We need 2 structures for each shader based on the constant buffers, of course. So for simple color, you have one that stores all 3 matrices. For color selected, you've got one for view and projection, and you've got one for the world and the color. So here's the thing. Basically, what we need to do is the input layout remains the same, so we don't really have to change that. So what we do is now then we both compile both the vertex and pixel shader for each of them. So this is for color selected. You've got, so they're stored here, the vertex shader and the pixel shader, and then you do that for, oh, sorry, I misspoke. Yeah, so first the vertex shader for each shader file. So color selected here, simple color here. You create the shaders and store them in the handles that we had. Input layout is the same, so no problem. And then the pixel shaders again for both. So we define two separate handles for the pixel shaders also. Unit pyramid is the one that we're going to go for. So after that, we have the buffers declared appropriately. Right here, this is the data structure for simple color, data structure for color selected, and the first one and now the world color one. Initialize the world matrices, it's pretty straightforward. And okay, so over here, to start with the first shader, so the first two objects are going to use color selected, so we connect the buffers to the appropriate rendering pipeline and then hook up your vertex and pixel shader. Then you send in the data as we did before and you render it right here. Now we need to change the shader. So what we do is we just again update the constant buffer with the simple color shader buffer, and again just hook up the vertex and pixel shaders of the simple color, and other than that again we just create the data and send it over as normal. So you've got those four vertex buffers out there. Sorry, four models out there. Sorry, it's been a long day. All right. So as far as the further work is concerned, you can see that in this one as well as question 3, I am using a single model pointer, and I think the clear advantage of that is basically that if you have two pointers pointing to the same data, and if you need to change one of the objects data, the other one will also change. So that's obviously not something that we would want. Say the world matrix, the one needs to change, and if you have two stationary objects and you want one of them to move, if we had two pointers pointing to the same thing, it would start moving both objects. So the reason why having a single pointer is better is, you have control over your data. You don't have two things pointing to the same data. So it reduces bugs. For the second problem, based on what I've done, basically a shader class for me would look like this. So you would have your handles to the vertex and pixel shaders. You would have an input layout description, and this would probably be again a structure that is just that is specific to the sort of constant buffer, the sort of shader constant that we have in HLSL code. And this, of course, is going to be our constant buffer. So upon construction, you just pass in a device and you pass in your path to the shader. So we would compile both the vertex and pixel shaders here and also create them for the device that's been passed in. And you could also initialize the constant buffer here with the size of this particular structure. And then this one right here is so we've been updating the data of constant buffers at runtime. So that's what this function is for. So again, you pass in a device context and you pass in whatever the new data that you have to do, and it'll just update all of this. And then finally, this is sort of based off of us changing the shaders at runtime. So again, just pass in a device and device context, sorry, and it sets this particular shader for that context at runtime. So I also have a bit of a shot at the last problem, but yeah, I couldn't really. I got the oh man, sorry. I got the vertices. I was able to figure out the vertices at all across the sphere based on the slices, but I wasn't able to figure out the windings. So yeah, I think that's a story for another day. For the Yeah, so this is basically hard coded for 3 vertical slices and 2 horizontal ones. So Yeah, I wasn't able to get the windings down properly. I can show you the way that I calculate the vertices though. It's right here. You calculate the number of vertices based on how many slices we have, and these are the angles of rotation. And then this loop actually starts off with the unit vector 0, 1, 0, rotates it a little bit about the z, that's dependent on the horizontal axis, then goes around and starts adding vertex data based on the number of vertical slices we have. When it's done around one horizontal ring, it'll rotate again, and it'll keep doing that until it gets all of them. So that was very long. Yeah, thank you so much for